Hi learners, welcome to SVC Microlearn. Through this portal, you can learn complex topics in science, technology, engineering, and mathematics in a very simple manner across various disciplines and genres. The learning will revolve around concept, design, and application associated with the topic. The exciting part is that you will receive an e-certificate upon successful completion of the topic. So what are you waiting for? Start exploring SVCE Microlearn today. Wishing you all a very happy learning experience. Welcome to the course titled State Machine Design for Low-Cost Automation. This is an interdisciplinary course with little bit of electronics and concepts associated with computer science. This course comes under the genre of automation with many applications in our day-to-day life. Let's first understand what a state machine is. To start with, consider the state machine as a black box containing one or more inputs through which electrical signals can be applied, with one or more outputs through which electrical signals can be obtained, and another input through which a clock pulse signal can be applied. It can go through various states which are different outputs that can be produced by the state machine. The state machine can move from one output state to another by applying a clock pulse. It can also move from one state to one of the many states by applying an appropriate input along with the clock pulse. For example, when the state machine is in output state of 0 and when a clock pulse is applied along with input 1, it can be designed to go to the output state of 1. Similarly, when the state machine is in output state of 0 and when a clock pulse is applied along with input 2, it can be designed to go to the output state of 2. You may be now wondering, what decides the number of inputs and the number of output states in a state machine? We shall understand this clearly with an example. Let's take the example of a toy vending machine. In this machine, when a coin with a value of 10 is dropped in the coin slot, it dispenses the big teddy bear. When the coin with a value of 5 is dropped in the coin slot, it dispenses the smaller one. Now let's see the operation of this toy vending machine in the form of a diagram. This diagram is known as the state diagram. From the state diagram, we can observe that there are three possible input-output conditions. The coin slot receiving no coin is considered as input 0. The coin slot receiving a coin with a value of 10 is considered as input 1. And the coin slot receiving a coin with a value of 5 is considered as input 2. Similarly, the toy vending machine not dispensing any toy is considered as the output state 0, wherein the toy vending machine is idle. The toy vending machine dispensing the big teddy bear is considered as the output state 1, and the toy vending machine dispensing the small teddy bear is considered as the output state 2. The operation of the toy vending machine can be easily understood with the help of the state diagram. When the toy vending machine is in its idle state and no coin is received through its coin slot, that is, when the input is 0, it remains in the idle state itself, that is, in the output state 0. While in idle state, if the coin slot receives a coin with a value of 10, that is, when the input is 1, then the toy vending machine dispenses the big teddy bear by going to output state 1. Similarly, while in idle state, if the coin slot receives a coin with a value of 5, that is, when the input is 2, then the toy vending machine dispenses the small teddy bear by going to the output state 2. Thus, the state diagram gives a complete picture of the operation of the toy vending machine. Let's add some more transitions to this state diagram so that it covers all possible input-output conditions. After dispensing the toys in state 1 and 2, if no coin is inserted, then the state machine has to go to the idle state during the next clock pulse. This is shown on the screen. Also, we shall impose a condition that a coin will be accepted for dispensing the toy only when the TDM is in idle state. Thus, while the TDM is in state 1 or state 2, whether a coin is inserted or not, it will be made to go to the idle state or state 0. Now this state diagram shown on the screen covers the complete operation of the state machine that is going to act as a controller for the toy vending machine. We will now make the state diagram visually simple and clear so that we can embark on the design. As a first step, let's remove all clock pulses shown, as they are anyway needed by default to effect the transitions and need not be shown explicitly. Next, we will indicate the input and outputs with decimal numbers rather than text labels. The last step will be to convert these decimal numbers into a binary format, as we will be using some digital circuits that can only recognize binary numbers. Let's first convert the inputs into binary and also the outputs into binary. We are now ready with the final state diagram, and let's go ahead to implement it as a hardware or circuit that will act as a controller for the toy vending machine. You must have observed that when the inputs and outputs in the decimal were converted into binary format, they became a binary number with a 2-bit representation. Thus, the inputs and outputs with a decimal value of 0, 1 and 2 get transformed into a 2-bit binary equivalent of 00, 01 and 10 respectively. Since the binary number is 2-bit, we will represent the bits of the binary number with subscripts 0 and 1 to indicate the least significant bit and the most significant bit. The inputs will be then 2 bits with labels of I0 and I1. Similarly, the outputs will also be 2 bits with labels Q0 and Q1. The state machine controller for our toy vending machine will now have 2 input lines for applying the binary inputs I0 and I1, 2 output lines for producing the 2 outputs Q0 and Q1. It will also have 1 clock pulse input. To implement this in the form of a hardware circuit, we need some building blocks. The easiest way to build the state machine is by using the JK flip-flop as a building block. But we need 2 of them, as the state machine needs to produce a 2-bit output. To differentiate these 2 flip-flops, we will use the subscripts 0 and 1. The output of the state machine will be taken from the Q0 and Q1 outputs of the 2 flip-flops. Let's start the design. The first step is to create a table known as the state table or the state transition table. This is easily derived from the state diagram which we have created for our toy vending machine controller. Let's see now how to fill up the entries in the state transition table. When the state machine is in the output state of 0, 0 and when the input is 0, 0, then it remains in the output state of 0, 0 itself. Similarly, when the state machine is in the output state of 0, 0 and when the input is 0, 1, it goes to the output state of 0, 1 as shown by the arrow in the state diagram. In the same way, let's fill up the other entries in the state transition table. You may be now wondering, what are those entries labeled X in the state transition table? They are called as don't care conditions because you do not come across such inputs or outputs in the state diagram. Now let's take up one more example. When the state machine is in the output state of 1, 0 and when the input is 0, 1, it goes to the output state of 0, 0 as shown by the arrow in the state diagram. The same way, let's continue to fill up the rest of the entries in the state transition table. The last step is to extend the state transition table into a state excitation table by adding 4 more columns to it. These 4 columns are the inputs which we need to apply to the 2 JK flip-flops so that when we apply a clock pulse to them, they produce the proper output in accordance with the entries in the state transition table. Now let's see how to fill in the entries J0, K0 and J1, K1. To fill in the entries in the columns titled J0, J0, J1 and K1 in the state excitation table, we need to first start with the truth table of the JK flip-flop. A truth table gives the next output QM plus 1 of a flip-flop for a previous output QN and the inputs J and K applied to it. From the truth table, we can derive an excitation table which gives the inputs to be applied to the flip-flop in order to effect a transition from a previous output to a next required output. It should be noted that the previous output is the one before the application of clock and the next output is the one that is obtained after the application of clock, and they are shown in brown and pink color respectively. When we observe the 2 cases of the previous output and the next output being 0 in the truth table, we observe that the inputs are J is equal to 0 in both cases and K is 1 in one case and 0 in another. Hence the inputs to be applied are 0x, which means J should be 0 and K can be anything. Similarly, the inputs to be applied are 1x when the previous output is 0 and the next output required is a 1. Similarly, the inputs to be applied are x1 when the previous output is 1 and the next output required is a 0. Similarly, the inputs to be applied are x0 when the previous output is 1 and the next output is also required to be 1. The learners need not necessarily derive the excitation table as it always remains the same. We shall now use the excitation table of the flip-flop to fill in the entries in the state excitation table of the toy vending machine controller. Consider the previous state of 0 and the next state of 0 for the flip-flop 0. Built on the excitation table, we know that the JK input to be applied is 0x. We can fill in this entry in the state excitation table. Similarly, we can fill in the same increase for all similar transitions for the 0th flip-flop. Now consider the previous state of 0 and the next state of 0 for flip-flop 1. Based on the excitation table, we fill in the input to be applied as 0x. We can fill in the same entries for all similar transition for the first flip-flop. In a similar manner, in the state excitation table, all increase can be filled up. You may come across in the state excitation table a don't care in the next output. In such cases, mark both J and K inputs also as don't care in the state excitation table. Now the state excitation table is complete in all aspects. From the state excitation table, we will make the increase in the Karnaugh map or the K map and get the Boolean expressions pertaining to the 4 inputs of the flip-flops, namely J0, K0, J1 and K1. Let's first make the increase pertaining to the input J0. You may observe that the entries are either 1s or 0s or don't cares, which are got from the state excitation table. The idea is to form the highest possible combination of 1s in the K map so as to get the most minimal expression. We may combine the 1s with the don't cares to form the combinations. In the first K map, the biggest combination possible is a quad as shown. From the quad, we get the Boolean expression for J0 as J0 is equal to I0 ANDed with Q1 complement as shown on the screen. Similarly, let us now make the increase for J1. In this, again, the highest combination is a quad that can be formed by rolling the K map so that the top row meets the bottom row. From the quad thus formed, we get the expression for J1 as I1 ANDed with Q0 complement. Next, we shall make the entries for K0. In this, the highest possible combination is all the 16 entries, and hence the expression turns out to be K0 is equal to 1. Similarly, we can make the entries for K1. In this too, the highest possible combination is all the 16 entries, and hence the expression is K1 is equal to 1. If you are new to forming the Boolean expression from the combinations in a K map, refer to any standard text on digital electronic principles and you will understand it very easily. We are now just one step before the last in the design. The last step is to convert these Boolean expressions into a circuit form. As mentioned earlier, we need 2 JK flip-flops to implement the state machine that will act as a controller for the toy vending machine. You can observe on the screen the 2 flip-flops available in the integrated circuit 74HC73 that will be used for this purpose. Let's first connect the 2 clock inputs of the flip-flops together and connect them to the clock source. This clock source is expected to generate the clock pulse that will trigger the flip-flops, which will then produce an output based on its past output and the applied input. Now let's do the connections based on the Boolean expressions we derived from the Karnaugh map. We will first take the 2 expressions where K0 and K1 are equal to 1. This is implemented in the circuit by tying up the K0 and K1 terminals of the flip-flops to a logic high or 1, which has an electrical equivalent of 5 volts. Next, we will take the expression J0 is equal to I0 ANDed with the complement of Q1. To implement this, we need 2 gates, an inverter to complement or invert Q1 into Q1 complement, and then to AND it with the input I0. This is shown on the screen. It may be noted that we use the integrated circuit 74HC04 for the inverter and the integrated circuit 74HC08 for the AND gate. Next, we will take the expression J1 is equal to I1 ANDed with the complement of Q0. To implement this, we need again one more inverter gate or NOT gate and an AND gate. The inverter gate will complement or invert Q0 into Q0 complement, and the AND gate will AND it with the input I1. This is shown on the screen. Now let's apply a strategy to minimize the circuit. The J-gate flip-flop offers another output which is the complement of its output. We can use these complementary outputs available in the two flip-flops instead of using the two inverters. This will save on the cost of procuring the inverter integrated circuit. By replacing the inverters with the signal tapped from the complementary output, we have the final circuit as shown on the screen. We shall now test this circuit for its operation. The circuit design will be now tested for proper operation using Tinkercad. The two slide switches I0 and I1 will be used to simulate the dropping of the coins, and the two LEDs Q0 and Q1 will be used to simulate the output state of the toy vending machine. Also, we will apply the clock pulse manually to a push button switch to enable us to see the transitions clearly, whereas in reality, we will be applied continuously from a clock generator. Now let us verify the operation. When I0 and I1 are both 0, and then the clock pulse is applied to the escape machine while it is in the idle state of 0, 0, you will find that it continues to remain in the hidden state. Similarly, when I0 is 1 and the I1 is 0, and when the clock pulse is applied while the escape machine is in idle state, it goes to the new state of 0, 1. While in this state, the next clock pulse applied will make the escape machine go to the idle state of 0, 0 again. Now when I0 is 0 and I1 is 1 while the escape machine is in idle state, amid the clock pulse is applied, you will find that the escape machine goes to the new state of 1, 0. While in this state, the next clock pulse applied to it will make it go back to the idle state. Thus, the design is verified and found to be correct. At this point of time, if you have some questions like how two switches can be used to simulate the dropping of the coins, and how, with the indication shown by the LEDs, they can dispense the teddy bear in a toy vending machine, take answer for these questions through our next course titled Design of Interfaces for Low-Cost Automation, offered by SVC Microlearn. Hi learner, hope you enjoyed the course. If you wish to get the certificate, click the assessment link given in the description. Complete the assessment and get your certificate of learning. Looking forward to see you in the next course offered by SVC Microlearn. Until then, happy learning.